So, so this is a mini course on Thurston theory, and what is that? So the real question is how to characterize. My dad was a topologist thinking about complex dynamics, and so there's a natural thing thinking about that, which is how to characterize rational maps topologically. So what does that mean? So what is a rational map as a topological object? It's some map from the Riemann sphere to itself. And you want to know, extract some topological data and see to what extent that determines the map. So it doesn't take very much thinking to realize the importance of the post-critical set, the forward orbit of the critical values, and that it's a lot easier to think about in the case when this is finite. This is the easiest case. I should say it's an ongoing challenge, which Hubbard was referring to in his talk, to extend to more general cases for this post-critical set, or for more to more general types of maps. For instance, transcendental maps. Like a lot of the pictures that I'm going to draw look very similar to the ones that Bernhard Reinke was drawing for transcendental maps, and there are some partial results about how you can do similar characterizations in that setting, but I don't want to summarize the whole thing. It's an ongoing challenge. There's some progress, but there's still much more to be done. But for this talk, I want to restrict to the case of finite sets of P. And so what is this map? So it's a branched map. The branch points are contained in P. And as we've seen a few times, it's natural to restrict to a case where it's actually a covering map. And to make it an actual covering map, let's remove the whole post-critical set. And then we have this covering where we remove the pre-image of that. I'm going to use some notation. T1 is just the inverse image of T0 here. And F here is now not branch covering, but is an actual cover. But now that we've done this, now we have two different surfaces, both punctured spheres, but two different surfaces and two different maps between them. And to get actual dynamics, you either need a map from some space to itself or two maps between two different spaces. And so we'll introduce there's a second natural map here, which is an inclusion map. So P1 contains P0, so the complement of P1 is contained in the complement of P0. So this is some other map. And then we want to make it more topological. We don't want to pin down the exact map. So the natural thing to do topologically is to consider this map, this inclusion, I, up to homotopy or isotopy. These are equivalent, but not in an obvious way. But they are equivalent. And so then and once we've done that, we can also now forget about the complex structure. So really we have some map from some punctured sphere, two different maps between two different punctured spheres. Let me relabel them. And one of them is a covering map, and one of them some other map, which we're only considering up to homotopy. And the question is, when is this, this initial question, is given this topological data, when can we rigidify it? When can we find an actual rational map that is equivalent to this under sort of a natural notion of equivalence? This is not quite the language that it's usually stated in, but it's it's equivalent to it. Right. Yeah, so in terminology, like this kind of data, two different spaces, two different maps, one of them is a covering map. So if I don't require one of them as a covering map, this is what's just called a correspondence. Here would be a topological correspondence. And if we require pi to be one of these to be covering map, this, like, I think at least 5 different names for this. The name I'll use is virtual endomorphism. Because, among other things, it gives a virtual endomorphism in the usual sense of the fundamental group of these spaces. Great. So, how to characterize this? When given this data, these two maps between these two surfaces, when is it equivalent to something like this? So there's an easy abstraction, which is contracting or expanding, depending how you think about it. So if we think about it in these terms, if we have an actual rational map, there's a natural hyperbolic metric on here. There's a natural hyperbolic metric on here. And this is actually a covering map. And then this is an inclusion of hyperbolic surfaces, so it cannot be expanding. So, if we go backwards by F and forwards by I, to the extent that's well defined. I mean, of course, there are multiple preimages here, but picking local lifts and mapping it forwards, this is contracting just by the Schwarz lemma with respect to this hyperbolic metric. Or if the more usual thing is to look at the dynamics on the Julia set, which is always contained in the image of I, so it can go backwards by I and then forwards by F, and that one is expanding, just depending which way we think about the dynamics. And this is shows up algebraically in a natural way as well. It's also Volodya referred to it in his talk as the contraction condition. You can also see it in a purely topological way, and in particular in this setting, there are going to be asterisks on various theorems, but this is equivalent in most cases to there being to saying F has no Levy cycles. No cycles of curves that are mapped to each other in a way that would obviously obstruct this being expanding or this one being contracting. Right, and so that's one. This is one constraint that to whether when F is equivalent, when an F like this is equivalent, or this virtual endomorphism is equivalent to a rational map, is that you can't have Levy cycles, or equivalently, this is contracting or expanding. I'll put a little asterisk on here because basically to avoid some Levy cycle cases, I believe. And I believe this was presumably similar things were known earlier, but I don't know an earlier reference than Bartoldi and Dudko. So this is an easy abstraction to being a rational map, but on the other hand, it's not enough in all cases. It is enough this was the contents of Sylvia Levy's thesis, is enough in many cases for polynomials or for degree 2 maps, but it's not enough in general. And so we want to understand more, more concretely. And really, there are two different answers. So there, I'm going to explain there's a negative criterion and obstruction due to my father, hence the name Thurston theory. And then there's a more recent, but also kind of less satisfactory in some ways, that I want to focus on today. I will mention this one, but I won't go into depth there. But before I get into this, I want to, this is maybe question 1 of the theory, but maybe question 0 of the theory is how to understand this data. How to actually like draw pictures of it. And this is going to relate to the graphs that were showing up in the title and on the title slide. I'm also happy to, any questions at any point, please feel free to speak up. Right, so this data, so, we have a punctured sphere. Let me take a particular rational map just for concreteness, one of my favorites. F of z is 1 plus c squared over 1 minus c squared, which the post-critical, the 0 and infinity are the critical points. 0 maps to 1, which maps to infinity, which maps to -1, which maps back to infinity. And so this part here is the post-critical set. And so, this is a portion of the theory that's kind of trivial, but that makes it easier to draw. And so we have the sphere minus infinity, 1 and -1. The plane -1 and -1, and then we have this covering map, and this was P0 in my notation, and then if I look at the inverse image, I also include 0, so it's also easy to draw. So this is the data that we have here. And there's really two maps here. One is the inclusion map and one is the covering map. And the covering map is doing something, wrapping around some ways, like how to draw a picture of that. And one key is that we're only considering, like, a covering map is basically a homotopical thing, and this is we're only care about it up to homotopy for the classification theorem. And so we can pass to a spine, which means a graph that is a deformation retract of these punctured spheres. These are, punctured surfaces have particular simple homotopy types. Their free group is a fundamental group. And so there can be modeled by one-dimensional CW complexes. And so I want to take this graph in here. And now I look at its inverse image, and the inverse image is punctured at -1, 0, 1, and still infinity. And 0 maps to 1. I got my notes backwards, so I'll work it out on the spot. So, yes, go. So you see a thing like this. Sorry. Meant to distinguish the two nodes of my initial graph. One of them you see green, red, blue, and the other see red, green, blue in counterclockwise order. And so that's what I used to label them back here. And now I'm orienting everything from solid to hollow. And you can convince yourself that this is the right thing. For instance, 0 is supposed to map to 1 with degree 2. And so around the edge region 1, we see green and red. And so we're mapping with degree 2. So we're supposed to see green, red, green, red. I'm hearing a little bit of an echo. Thank you. Yeah. Okay, thank you. Right, and so instead of trying to describe a map between surfaces, you can instead look at this map between graphs. And so what we get is capturing the data. So replace S2 minus this set with some graph gamma 0 and S2 minus P1 with gamma 1, which is this one's supposed to be covering match, so this one's supposed to be the inverse image of gamma 0. And then we still have the covering map going that way. That still works perfectly well. So we have this one covering, and I'm using colors so that so this one preserves colors. And then we're supposed to have a virtual endomorphism, so we're supposed to have another one. And this is from I and the deformation rate. What else do I want to say here? Right, and really this one's only defined up to homotopy. And well, there are little asterisks here. For this to actually cover all the data, you need some going back here. This was defined up to homotopy or isotopy. So if two inclusions are homotopic, then they're also isotopic, more or less, if they're orientation preserving. However, you could, if I only look at what happens on pi 1, there are other maps that don't come from inclusions. So you do need some extra data about like the peripheral structure, like what the loops running around the punctures, or equivalently, some data about a ribbon graph, like some data giving you a little thickening of this to a surface. And so we need some extra data there, and this should be a ribbon inclusion. But this turns out not to actually matter for the criteria for whether or not it's rational. And the other thing I wanted to point out was that this is actually closely related to the kind of data that Laurent was showing in his talk this morning. So so you can take any graph you want as your spine. So instead of this graph, with 2 nodes. If I'm thinking about it as a generator for pi1, I could instead take a graph with just 1 vertex. So this is what's called a rose graph. And it naturally gives generators for the fundamental group. And then if I take the inverse image, its inverse image is no longer a rose graph, but it will have 2 vertices. And on the other hand, this inverse image is very closely related to what's called the dual Moor diagram. So Laurent was not overloading you with different representations. There are many. It's helpful to switch between them. But he was drawing the Moor diagram. This is the dual Moor diagram. These are also the pictures that Bernhard was drawing in his talk. They kind of fit more naturally with the geometry of what's going on, but of course they're each helpful for different reasons. So this is basically a version of the dual Moor diagram. And on the one hand, the graphs we're considering are a little more general because I could have 2 vertices and not just 1. I didn't need a rose graph. And on the other hand, if thinking about it algebraically in terms of bisets is more general because I only get certain generating sets for pi1 thinking about it this way. And for instance, I couldn't get an embedded spine and have redundant generators, and that's perfectly fine from the algebraic point of view. So both have natural generalizations, but they have a large overlap. Great. So, right. So those are the pictures we're going to think about. And I wanted to give, I think there were 2 answers, one negative and one positive. Let me briefly review the negative answer. Certainly not going to prove anything before stating the positive one. So the negative characterization, which is more familiar. So this comes, I went on this whole spiel about graphs and so forth, and I actually want to go back and think about it in terms of the surfaces. So you think about iteration on Teichmüller space. So you have these 2 surfaces, 2 maps between them. And like I'm looking for something where I have 2 maps which are both conformal. Well, I can start off by doing that by picking some conformal structure on this first surface over here and seeing what I can do with that. So I can pull it back by this map pi, and I get some other structure sitting inside this one. For instance, this this one that covers this one exactly in the hyperbolic metric, and then I can fill in those punctures and get another. Sorry, not that space, but in the Teichmüller space of those spaces. And then I can fill those in, fill in the punctures. And forget about the extra punctures that I had over here and think about what I have down here. And it's so this one is basically an isometry well, to its image, which is not everything. And then this one is a map between complex manifolds. The Teichmuller metric is also the Kobayashi metric, and so it's automatically non-expanding. And then a little bit of analysis, this is not the hard part of the theorem, is that it's basically a contraction. So not that function itself, but if you square it, that function is a contraction. This pullback map is a contraction with respect to the Teichmuller metric. Now, this is one of the places where I need a little asterisk here. Here, for instance, if F, the original map F, was not lattice. Basically, there are cases where everything is covered by the sphere, by the torus, and in those cases, it's instead an isometry. But in other cases, it's necessarily a contraction. And so, okay, so we want to think about like when, and we're looking for fixed points. A fixed point basically is the solution to the rigidification problem of turning this topological data into something geometric, some rational map. And so great, it's a contraction mapping. It should have a fixed point. The issue is that this is not uniform. Like even in cases where it does have a fixed point, this is just definitely not a uniform contraction. So you need to work some more. And you think about cases where there obviously cannot be a fixed point. So there are some obvious obstructions which come from basically annuli getting thicker. So if I have some punctured surface and I have some multi-curve on it, and really this should be a weighted multi-curve, but I don't want to get into it too much, then you have the inverse image of that, and that's, you have something with more punctures, and you'll have multiple multiple components over here. And keep track of everything, and then you erase some of the punctures, and now you get another set of, you get the same curves now on the same sphere. And if you're unlucky, maybe you get like you'll usually get some trivial components and things surrounding punctures and so forth. But maybe like a little annulus here, you pull it back and you look at the modulus here and you push it forward and you look at the modulus here. Maybe it ends up getting thicker and thicker and thicker. You're heading off in this iteration. You're getting thicker and thicker annuli, and so you're heading off to infinity in Teichmuller space, and you necessarily cannot have a fixed point in the interior. And the theorem is that that's enough, that written up nicely by Doherty and Hubbard, is that F is equivalent, given a branch self-cover, it's equivalent to a rational map. If and only if there is no obstructing multi-curve, which means a curve that's getting thicker and thicker in this sense, which you can turn into a very concrete condition about eigenvalues of some positive matrix, but really it's about annuli getting thicker. And again, there's the same asterisk that F is not lattice, which are cases you can treat separately. Great. the problem, and the problem that this raises is, can you state this positively? Like, you notice that this is of the form, like you have a rational map. To check that it's a rational map, you need to show there's no obstructing multicurves, which, in principle means you need to look at all possible multicurves and check them. You can do shortcuts in many cases, but like this makes it really easy to show something's not a rational map. You just need to find that multicurve, but it doesn't make it easy to show something is a rational map. You need to do some more work. So can you give a combinatorial certificate that it shows that F is rational? So one way to approach this is to go back to my easy abstraction about contracting and expanding. Like, I wanted to see what, like, I know that if it is rational, then the hyperbolic metric gets contracted pulled back under cover and then mapping forward or expanded the other direction. But hyperbolic metrics aren't very combinatorial. So how to make this contracting condition combinatorial? So we'll get up to this problem, but let's first answer this one. So, and for that, I want to go back to the graphs there. It's equivalently, maybe after iteration, I'm not actually positive whether iteration is necessary here, to looking at these graphs. To find a graph gamma 0 and a metric on gamma 0, it's pullback metric on gamma 1 and P in the homotopy class, so that P is contracting. The Lipschitz stretch factor of the maximum over all points in gamma 1 of the derivative of phi, that this is strictly less than 1. And if this happens, it's easy to think, for instance, if you think in terms of Levy cycles, it's easy to see that shows that Levy cycles don't exist. On the other hand, to go the other direction, if I claim that this is an if and only if, to go the other direction, you look at things like the limit as n goes to infinity of the Lipschitz stretch factor of the stretch factor of the nth iterate, and really not, I don't quite want that actually. So I want the minimal stretch factor in the homotopy class of that nth iterate, and I want this limit, and raise it to 1 over n to be well behaved. I want that limit to be less than 1. And this is independent of the model by sort of general combinatorial things. if I change gamma 0, if I pick some different spine for my space, or pick some different metric here, when I start iterating, any of those changes just vanish in the limit, and I'll get this some natural contraction factor, which is less than 1, if and only if it's contracting, and then there's some more work to show that that's equivalent to there being no Levy cycle. So this was.
Sorry, what is your infimum
Yep.
taken? What's the infimum taking over?
Sorry, in the homotopy class.
Okay, homotopy class. All right.
That's my bracket. Sorry.
All right. Thank you.
Another thing I didn't say is exactly what I mean by iterating, and that's about iterating a correspondence. Let me just draw the picture here. We have these two maps. If I want to compose two correspondences, the way you compose correspondences is by taking the pullback, which is not very well behaved in general, but because this is a covering map, this will also be a covering map. And so this is a covering map, and so you still get sort of a nice correspondence. And this one here is the map that I was calling B2. This is what I mean by iterating. But it's just the right way to iterate correspondences rather than maps. And for the same usual dynamical reasons, this limit is independent of the model and controls whether it's contracting. I should also say, I'm making a combinatorial. This is making it more combinatorial. I can prove that it's less than 1 by giving an explicit map, explicit graphs, and it maps so that that's a contraction. And of course, there are also more combinatorial ways to do it. And this is the theory of bisets and so forth, and finding the nucleus there. Laurent has these great programs that will answer this for you very quickly in practice. But on the other hand, this was the condition that was not sufficient. This is just about the contracting condition, equivalent to there being Levy cycles, and we want something that assures us that F is rational. So we want something that goes further and gives us this further thing, this more like looking at annuli getting thicker, which in general is a somewhat more complicated thing involving eigenvalues. And so I wanted to answer that, I wanted to recast this kind of criterion. There being no obstructions, like what happens when their annuli get fatter and fatter? The modulus of these annuli are going to 0 in this iteration. Or we can also look at it in terms of extremal length. The extremal length is going to 0 in this iteration. So no obstructions is also equivalent to saying that the extremal length of curves gets larger under iteration. And here I should really add I should say a little bit more what I mean. So for hyperbolic maps, and if I want to get something that's actually true, I want to actually remove a disk. So I have some map here, and instead of puncturing it, I want to actually look at some finite region and remove, say, some level set in the Butcher coordinates. And now I take the inverse image of that. I'll get something else with another hole, in this case around 0 for the map that I had before, and then I include it. And the image of the inclusion is some proper subsurface here. This proper subsurface, because I took some level set in the Butcher coordinates and things are going the other direction, things attract very quickly to my super attracting cycles. And so going backwards, I'll be removing more and more. So I get a smaller subsurface, which means all annuli in the smaller subsurface are larger, which means that extremal lengths were increasing. And it's not that hard, but it does require some work to show that they're getting larger at some definite rate when you go backwards like this. And so what you want, and so we want to look at something like this, where instead of looking at Lipschitz stretch, we want to look at how extremal length behaves under backwards iteration. So we want some sort of combinatorial model for extremal length. And that also comes from graphs with a metric. And so you take some graph with some metric here, give the edges, give some numbers to the edges here. Let me just give them all. Let me give them some different lengths here. And I want to thicken it. Imagine thickening it to a little actual surface here, a conformal graph, a conformal thing here, where each edge got replaced with a little rectangle of width, epsilon, and length, some number given by the metric. So I have some metric here, and I want to think about the number on the edge as being some sort of conformal length, and I thicken it to a little rectangle, and then I patch them up somehow at the vertices in a natural way. And then not so hard theorem is that the extremal length on this thickened surface, and epsilon of gamma, is up to scale depending only on gamma, on epsilon. I want the extremal length of some curve, which means some loop running around on the surface, and maybe it's a multi-loop, something like this. And it's the sum over the edges of the number of times the curve runs over the edge squared times alpha of e. Anyway, some simple combinatorial function on that. And now I want to try to capture. So this is extremal length. This is a combinatorial model for extremal length, and I want to model this thing about extremal length getting larger under iteration. So at this point, let me jump ahead and state the actual theorem here, which is that f a hyperbolic, meaning every hyperbolic GCF branch self-cover So this is again a map from the sphere to itself with some, and hyperbolic here means that there's a branch point in every cycle. If and only if the corresponding graph virtual endomorphism to maps like this has a metric alpha on gamma 0, alpha 0 on gamma 0, pullback metric alpha 1 on gamma 1, and some representative phi in the homotopy class so that the extremal length doesn't increase, and then it turns out that you can state in a purely positive way. You look at, okay, so if I were looking at the Lipschitz energy, I'd be looking at the supremum, like any point here, how much it gets stretched, and ignoring some points where the derivative is not defined. So instead, I'm going to look over points in the target space, points over here, and then sum over all three images of the derivative. And this should be less than 1. And for this to actually be correct, this should be true after iteration. There are definitely cases where of concrete rational maps where you do need to iterate. But on the other hand, after enough iterates, you will be able to find this model.
Excuse me, Dylan, what's your statement? Are you saying that, like, I don't think your first phrase is like a complete sentence?
F is a hyperbolic, right, yes. I forgot to say that this complicated statement, I forgot to say the simple one first. This was the setting. This is equivalent to F is rational. Thank you. That was the question?
It sounds
F is, meaning F is equivalent to rational map. What was that?
It's okay.
Yeah, okay, good. Okay. Great. Right, and there are various variations of this, like, after iteration, I said you can find some metric and some representative so that this is true, but really this is just like in the case of the stretching, this is independent of the representative. So really what's going on is that for sort of general dynamical principles, if you look, there's the sort of amount you stretch asymptotically is independent of your representative. So concretely, if you look at so I want to look at this energy, this weird sum of derivatives, but infimized over a homotopy class of some iterates. And now I'm iterating in more and more, so I should take the limit as n goes to infinity, and I should normalize things so that I expect it to stay bounded. This is independent of the model of the choice of gamma 0, gamma 1, and the metric. Well, gamma 1 really, once you've chosen gamma 0, there's no choice. This is necessarily the cover of gamma 0, but if I change gamma 0, gamma 1 changes. So I have the virtual endomorphism. And this is independent of how I pick it.
Dylan?
And then,
Dylan?
yes?
Do you need in your statement pi somewhere? I think that everything is formulated in theorem. In the theorem, everything is formulated in terms of phi.
I need pi because of this after iteration bit. Right, so this here,
no, but, is it...
let me say this one here. So, actually, let me go back to this picture here. Like, I'm only interested in the energies of these maps phi, but in order to define this map, I also needed the map pi. And furthermore, I I picked some metric on here, and then in order to make this correct, I do the natural thing, which is to take the pullback metric with respect to that covering metric on here, and then look at this map from this metric graph to this metric graph.
Okay, thanks.
Misha, that was your question?
Okay, thanks, yeah.
So it's sort of implicitly appearing in how this iteration is happening. Great. Yeah, and then the other part of this is that this is related to how quick, like extremal lengths necessarily get larger and larger for rational maps. I'm looking at the asymptotic growth rate of that, which is going to be greater than 1. And if it's, right, the map's going the other way. In any case, like this limiting value, if this limiting value is less than 1, then some finite term here is less than 1, and then you can find a concrete representative to give you your combinatorial proof that you have a branched self-cover. Great. And just to connect up to this extremal length, which is a key part of the proof here. I had this definition of extremal length, and this is a separate sort of non-dynamical theorem. So I have two metric graphs like this, and some map feed between them. So this funny energy that I wrote down, and really the infimum of that over the homotopy class, is equal to the supremum over all curves on gamma 1 of a ratio of extremal lengths. I have some curve C sitting inside here, and that gives me a curve sitting inside here as well, and I can compare the extremal lengths of these two curves. So relating extremal lengths relates to this one, and this is also helpful in that this is a supremum and this is an infimum, and so if I can get bounds either directions by either finding a curve or finding an actual map satisfying this finite condition on sums of derivatives. And so this is like a combinatorial theorem, not necessarily so easy, but it's related. Let me just give everything's easier when you're only thinking about contractions. So there's a much easier to see theorem that the minimum Lipschitz stretch factor of a map between metric graphs is equal to the maximum amount that the lengths get stretched. Any questions on this?
Sorry, can I ask in your theorem?
Yes.
When you say, just to make sure I understood, when you say a hyperbolic PCF branched self-cover, what exactly does hyperbolic mean here?
Hyperbolic, so in the usual way of saying it, without referring to these punctured spheres, I have a map like this, and hyperbolic with, where P contains all the branch points in this is invariant under forward integration, and hyperbolic means that there is a branch point of P in every cycle.
So it corresponds to hyperbolic rational maps in the dynamical sense. So.
Yeah, and it's unfortunate terminology because there's another condition which is asking that the orbifold of the map be hyperbolic, which is, and I wish, so sorry, there's a little ambiguity in the terminology.
All right, thank you.
Yeah. Maybe I'll mention, there are, you can hope for more. So in progress is extend to cases, to a much weaker condition, basically when the Julia set is not the whole sphere. So instead of asking that there's a branch point in every cycle, I ask for the case when there is at least one branch point in one cycle. And the main annoyance here is that you need to use a theory of orbit graphs, which are probably more subtle than you think they are. But you need to use that theory, but in principle, this is straightforward. But I have not yet written up. Right. I did want to end with a challenge, which is improve the models. So if you look, and give a version that works without iteration. So if you look, there's this sort of, from an actual rational map, you get these surfaces and they're necessarily getting thinner and thinner, extremal lengths are necessarily going to 0. And then we take this model of it, which is this epsilon thickening of a graph. And this works well for some families of rational maps. I think in particular, the crochet maps, you shouldn't have to iterate, although that's not proved. But if, for instance, your map, like the Julia set was a Sierpinski carpet, it would certainly be hyperbolic. This theorem is still true after iteration, but this epsilon thickening of a graph doesn't look very much at all like what you get in this construction with the Julia set. So like this, it's just not a very good model for the thickening of the Julia set. And so I want more flexible models to somehow work with iteration and work on the nose like that. And there's also, we also mention that there's a more general family of energies. EPQ for 1, P and Q between 1 and infinity, where, for instance, this one is the Lipschitz energy, this one is the square root of the thing I called embedding energy, which was an unusual one, but other ones are less unusual, like this one is the square root of the extremal length. And then there are also asymptotic EPP for any 1 less than or equal to P less than or equal to infinity, where P equals infinity controlled whether this contracting behavior, which was crucial to do much of anything. E22 was the one that controls whether or not it's rational. And the critical, and another theorem, which should take another talk to fully unpack, is that the critical exponent for this is the Alforus regular conformal dimension. Anyway, and let me just draw a graph of that. So P is increasing this way. Here's this asymptotic EPP, and it doesn't increase as a function of p, and so at some point it crosses the value 1, and that point is the alpha is regular conformal dimension. And this is joint with Deb and Pilgrim. Okay, let me stop there. Thank you for your attention.
Thank you, Dylan. Are there any questions?
Yes, hi Dylan. I have
Hi.
2 questions. So I guess one of the interesting things is to compute these things, and on the previous slide you had some infimum equal to some supremum, right? Yes.
Well, I had a couple of them. Yes, maybe, yes, this slide
That
I
seems
think
a
you're
very
referring to.
important one, and it looks very much like duality for a linear programming. So is there
Yes.
an interpretation of this? Just writing a linear program for the embedding and for the quotient of extremal length?
It is analogous. It is not quite the same because there's a kind of linear programming part. Like if you fix the combinatorics of the map, like which vertices map to which edges, then everything's basically a linear function. But actually, this one is better that way. But then there's combinatorial data of that choice of like you have a map between graphs, and so you're choosing which vertices go to which edges, and that's a combinatorial choice that makes it not quite a linear programming. However, the analogy is very helpful, and in particular, that's how I proved that is essentially by using analogies with linear programming.
So
right, and furthermore, by the way, this is also implemented. Like using this duality, you can actually find the minimum in this homotopy class.
So a related question is: do you have to choose gamma 0 carefully?
No, no. I mean, it depends how much you want to iterate. So this limit is independent of how you iterate, and it'll asymptotically be decreasing at some factor, which is independent of the map. However, it can make a big difference in how long you need to iterate. In that, like, you're decreasing at some rate, and maybe you're decreasing, like, you multiply by 0.95 each time. But if you start off something fairly high, then it takes a while to get below 1 and sort of rigorously prove that you're decreasing at that rate. I think you also encountered this, like where you're looking at these biset automata and like just seeing whether it's contracting, like, or looking at the size of the nucleus. That can depend a lot on what you choose as the basis for your biset. Is that correct, Paul?
Yes, it was. Well, I have another question. So it is known that the classical proof for Thurston theorem has analogies to the proof for hyperbolization of Haken manifolds. Do you anticipate that your positive proof or criterion will lead to some new proof for hyperbolization of manifolds?
So honestly, a lot of this was inspired by sort of known positive criteria in that case. I hadn't thought about that 3-manifold question. Like I was starting off thinking about, like, if I want to show a map as pseudo-Nosov, which is equivalent to showing that its mapping torus is hyperbolic, there's a positive criterion for, there's both a negative, there's an obstruction for that, which is basically equivalent to Levy cycles, and there's also a positive criterion of looking at certain train track maps, train tracks on the surface, and I was trying to find an analogy for that. I haven't thought about the full 3-manifold question, so there might be something to do there. I'm not sure. Right. That's actually interesting. Right. There are various positive criteria in general, but they're all not quite satisfactory, like angle structures and so forth.
Lasse has a question.
Yes. I'll think about it more. Yes.
I mean, I guess the obvious question is what happens, when the Julia set is everything, when every critical point is pre-periodic. You said in the case where there's at least one attracting cycle, there's a way to do a similar thing. So what if there are none?
What if there are none? Right, I have trouble seeing how to get any sort of combinatorial model. Like the Julia set's the whole sphere, and it's a little hard to see how to get any sort of combinatorial model for the Julia set that isn't just the sphere. So I guess I don't know what to do in that case.
What I find sort of striking about this is that there's this different setting of these expanding Thurston maps, where Daniel Meyer, Mario Bonk, various work and so on, where they kind of have the trouble in the other direction, or not trouble, but they haven't done the work in the other direction of kind of, and because they have got some kind of criteria as well. I can't really remember.
Right.
I don't really know this work very well, but they also look at these expanding Thurston maps and when are they equivalent to rational map, etc.
Right. And for them, it was somewhat easier, for instance, to find forward invariant curves, to find like nice subdivision rules in the case when the Julia set was the whole sphere. That's right. Yeah.
More questions?
I mean, in a sense, what we did was really, sort of cooked up so that the Julia set is a whole sphere to be sort of closer to Hennenfent's conjecture. So, I mean, it was sort of, intentionally sort of like this. But I have another question. So you had this sort of, I guess, this embedding energy, and then, this ratio of these extremal lengths. Where was it? Yeah, this one, exactly. And I mean, this looks actually to me very similar to Thurston's criterion on that there are no obstructions. I mean, like if you think about the spectral radius, being sort of like how modulus given by some obstructions degenerate, and can we kind of sort of interpret, this condition also, in terms of the Bill Thurston's condition on that there are no obstructions, or is that too naive?
One thing, right. I guess this energy, and in particular this theorem, and like even more particularly the inequality that this number is greater than or equal to this number without the infant soup, that was all cooked up like as a like you can think about that as sort of being arranged to rule out obstructions. So if you have something with embedding energy less than 1, then it's just from this inequality without an infant soup, which is actually quite easy. Well, yeah, which is much easier. Then you can immediately see there's no obstructions. Using essentially the same proof that there can't be obstructions for actual rational maps. Was that your question, Daniel?
Yeah. I mean, really, how? I mean, whether I don't know. Let's say the obstructed multi curves sort of really make an appearance in some fashion. That was really the question.
Yeah. And it's this inequality. Yeah.
Okay. Yeah. That was exactly my question. Mm-hmm.
So, Dylan, can I ask a question about your critical exponent on the last slide? So.
Yes.
So
yes,
you have this critical exponent, and in the usual thermodynamical formalism, so the dimension appears usually as a parameter that annihilates the pressure. So the pressure is 0. Is there a relation? Is there some thermodynamical interpretation of your critical exponent formula?
Yeah. And the answer is that I don't know how to do it. So a lot of things that look very familiar from the thermodynamical formalism. The thing that I don't know how to deal with from that point of view is that in order to get sort of correctness and get the correct thing here, I should take the infimum after iterating. And this is not a thing that people do when thinking about the thermodynamical formalism. Like you have something and you just iterate that. And so I don't know how to fit that exactly in that setting. On the other hand, I also think that this should be related to getting improved models. Like maybe if you improve models, you get something where you don't have to hone the top after iterating.
Thank you.
Okay.
Sorry, maybe just a quick question. So in the proof, do you go via Thurston obstructions in the classical sense, or does it, or is there a new proof to showing that the maps are equivalent?
There's one point where we need Thurston's obstruction, which is to go from saying that the iterate isn't obstructed to saying the map itself isn't obstructed. Mm-hmm. Otherwise, it's an entirely independent proof.
Okay.
So,
and the key thing, like one direction, like showing that you actually get a rational map, it's actually pretty easy. Well, you use quasi-conformal surgery in pretty standard ways.
If there are no other questions.
Yeah. Sorry, go ahead.
Or comments, we can thank the speaker again.